how can you use the equation of this quadratic function to predict end behavior? End behavior. So when we're asking about end behavior, what are we looking for? Just did that on your quiz. What quadrant does it start and finish in? Okay, so what can you tell me about this graph just by looking at it without using our graphing calculators? What do we know about this graph? Degree of 2, so meaning it is what? What kind of graph is this? A parabola. 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 Okay, so we know it's a parabola. What else could you tell me about this graph just by looking at it without using our graphing calculators? How do we know it opens up? Okay, and I'm going to give it a new, what's positive? The coefficient, and so we're going to call that the leading coefficient. Why would I call that a leading coefficient? Okay, so if I had it written like this, would 40 be the leading coefficient? With the highest degree. So the leading coefficient is the coefficient of the highest degree. So leading coefficient is positive. And so the leading coefficient is the one attached to that, the one you attach to the what? Let's try this again. It's the coefficient attached to the variable that you use to get your degree, the highest degree. Okay. Okay, so what else do you know about this graph just by looking at it? Is there anything else? Your y what? Your y-intercept is 40. And so what do we call 40? Does anyone know the name of 40? It's called the constant term. Why is it called the constant term? What's the definition of constant, Dean? Stays the same. So no matter what x is, will that term change? No, because there's no x to change it. So that's the constant term. So looking at this, we know this graph opens up. So if a graph opens up, no matter what the y-intercept or x-intercepts are, does it affect the behavior of the graph? So let's draw a few of them. So what if it opened like that, or like this, or like that? Okay. Does the behavior, are all of these graphs, no matter what the y-intercept is, are the behaviors the same? Yes, they're all going from 2 to 1. So all we need to look at for behavior is what? The name for it? Did you guys not catch what we just talked about? Okay, so so if this graph opens up, as long as it's quadratic and opens up, it has the same end behavior. It doesn't matter what these numbers are. So all we have to look at is, what tells me if it opens up? The leading coefficient. So how can you use the equation? So how can we use it? We just look at the leading coefficient. And that's going to be the same for linear functions. It's going to be the same for constant functions, quadratics, or cubics. All of them. And behavior, all we need to know is the leading coefficient sign. Yeah. Well, for end behavior, right? So even if it's here, eventually it's 1 and 2. Even though it passes through 3 and 4, its end behavior is 2 to 1. Yeah. So it would have to be downwards to have from 3 to 4. Okay. Oops. Moving on. Oh, lots to write here. Okay, if you have a highlighter, this would be a good time to pull it out. I'll get one too. Choose that color. I like that color. When a polynomial function is in standard form. Review, what's standard form? All these. y equals ax squared plus bx plus c. Remember, there's vertex form, there's factored form, and standard form. Standard is like general, right? Just like general. And all these.
Do we have to get it in standard?
No. Yeah. When a polynomial function is in standard form, everyone remember what a polynomial function is? It's amazing how much meaning can be in one short little sentence. Okay, what's a polynomial function? Gotta know our terms, right? So how did we know something was a polynomial function? Don't remember. Easy way to remember a polynomial function, because the definition I gave you kind of is wordy, is the exponents on the variable are all whole numbers. Does that help? No? Okay. Let me. Exponents on x, then we'll say, exponents on x, the variable x, okay, are whole numbers. What are whole numbers? What's a whole number? Jesse, did you say it? No? Where does whole number start? 0. Natural starts at 1. The whole, think of whole as a whole. Starts at the whole. Get it? I should have like totally explained that and did just no, but like seriously, that would really help. I should have thought of that earlier. Okay, 2 starts with the whole. Okay. Okay, so does that exponents on x are all whole numbers? So you can't have negatives, square roots, right? Does that help a little bit? And no dividing, just y equals x cubed, for example. Okay, so when we have polynomial functions in standard form, Jesse, the maximum number of x-intercepts is equal to the degree. So max number of x-intercepts is equal to the degree of the function. So for example, y equals, what did I have written there? 10x to the 9 plus whatever comes after. How many possible x-intercepts? 9 possible x-intercepts. Okay, the maximum number of turning points. We talked about this a little bit last day. Max number of turning points is 1 less than the degree. 1 less than the degree. It's not always equal to. It could be 0 turning points. So turning points are like mini maximum and minimum. So this graph has 2 because you have like, right, it's going to be a bump, a curve. So how many, if we had that function y equals 10x to the 9 plus whatever, how many possible turning points? 8 possible, 8 max turning points. Yeah, TPs. I'll probably end up writing them later. The degree and leading coefficient of the polynomial indicates the end behavior. We just talked about that. Yes. Use purple maybe? The degree, I'll go underlining. Degree and leading coefficient tells us end behavior. And constant term in the equation is the y-intercept. I wish I had a cooler, I don't know. Constant term is the y-intercept. So if I had y equals 3x squared plus x minus 3, what's the constant? Or what's the y-intercept? Negative 3 would be your y-intercept and constant term. Okay, one more quick thing. Linear and cubic have very similar behavior, end behavior, right? A linear graph versus cubic graph, very similar end behavior. Or basically the same, actually. Versus. Ready for an actual, oh, so all that stuff we just went through, those key ideas, super important. Okay. Whew. Oh, did I jump something?
No.
Where's the, I think your instructions are on the previous page. No? Oh. Oh, I went in the wrong order. Sorry, mixed up my notes. There you go. Okay, can you write odd functions at the top here? So what do you think is an odd function? What's an odd number? Start with that. 1, 3, 5. Okay, so an odd function, I'm going to give you a very limited definition of an odd function. There's a bigger definition. But the simple definition, Jesse, is an odd degree. So in our case, what type of graphs have odd degree? Linear and cubic. And then there's, so odd functions behave similarly, and even functions behave similarly. So odd, the leading coefficient is negative in this example for degree 1 and degree 3. And then the graph will go from 2 to 4. Okay. So it ends up in 4. If it ends up in 1, it's a positive leading coefficient. Go from 3 to 1. Is there anything else I wanted to add there? Nope. So the even functions, we only really cover one even function. So an even degree. What even function do we cover? Quadratic, 2. Right? Parabolas. The next one would be quartic functions. So what do you think a quartic function is? Degree 4. Yeah. And degree 4s are very similar in behavior to, so all even functions have the same end behavior. So we know parabola looks like this. A 4th degree looks like this. Okay, it could even look very similar to this guy, but that's what a quartic would look like. And power of 6, again, would have very similar end behavior. Right, the number of possible turning points is 1 less than a degree. So if this is degree 4, has a possible of 3 turning points. This is degree 2, 1 possible turning point. Degree 6, 1, 2, 3, 4, 5 possible turning points. Cool? Okay, so yeah. If we end up in 4, you'll notice if we, no matter what the function is, if we end up in 4, it's negative. Leading coefficient is negative, goes 3 to 4. If we end up in 1, it's positive. Easy. Okay, let's go through an actual example now. Okay, so this is what we want to do for each one. We're going to describe possible number of x-intercepts. We're not actually going to find them yet. Domain, y-intercept, range, and behavior, and possible number of turning points. So this guy, we'll make a list first to make it helpful. So we need to find possible x-intercept. We need to find y-intercept. We're going to find domain and range. Possible number of turning points, TPs, toilet papers, and end behavior. So your quiz will be like this tomorrow. Whenever you come to a function, the first thing you want to figure out is your degree, and so what type of graph you're dealing with. So this graph, linear. Good. Possible number of x-intercepts then, if it's linear. How many possible x-intercepts? 1. Yeah, it's equal to the degree. Possible equal to the same as the degree. Okay, y-intercept. What would be the y-intercept? -5, it's the constant term. Domain, we're dealing with a positive linear line. What would the domain be? X down in the reals, and range is always YER. Possible number of turning points. If the degree is 1, it would be 0 because it's 1 less than the degree. And end behavior. So is he going positive or negative? Looking at leading coefficient, positive. So it's going from 3 to 1. Quadrant 3 to quadrant 1. Right? Remember, what's the name of this right here? That 3. The leading coefficient, what else is he? In a line. Remember Math 10C? No. It starts with an S. Oh, the slope of the line, right? Positive slope, rises to the right. Okay, next one. So let's write this list again. I wonder if I should just, I'll write it again too. Okay, possible number of x-intercepts. How did you know that? The degree is 2, and so there's 2 possible. Okay, what's next on our list? The y-intercept. What is the y-intercept? 8, it's the constant. So that's our y-intercept. Next we did, let's come back to domain and range. And first look at number of possible turning points. How many possible 1? Good. And we also need, what else? Number of, end behavior. So how do we figure out end behavior? Look at the leading coefficient. It's a negative. So what does a negative quadratic look like? Opening down, so it's going from 3 to 4. Quadrant 3 to quadrant 4. Okay. All right, back to domain. Domain of any function is always x and element of the reals, right? Keeps going to the left and right. Now, the range, we're not going to go to the, we're just going to make it general, write it generally. Y is less than or equal to our max because it's opening down, it's going to have a maximum. We would use our calculators to figure out the maximum value. Or we could actually write it in factored form or vertex form. But right now we're just doing the general. Okay, do you want to do the last one on your own? Okay? Try the last one on your own. Okay, so possible number of x-intercepts? 3. It's a cubic, and it's positive leading coefficient, so it's going to look roughly something like that. It might even be like this. Okay, so in a cubic, it says number of possible turning points would be how many? 2. So it either can have 2. Here's an example with 2 turning points. Here's an example with 0. So you have no humps. I guess we can call them, I don't know. Has like local min and local max is what they are actually called. And this has no local min or max. Y-intercept is, okay, negative 10. Bring the sign with it. Domain, XER, thank you. Range. Okay, so for a cubic graph, it's very similar to a line. How far up and down will this go? Forever, so it is YER. And behavior, because it's a positive leading coefficient, it goes from quadrant 3 to quadrant 1. Good. We're almost done. Yeah, just the end of this page and then we're done. Okay, so do you want to try matching? And then we'll go over them. So match the function to the graph without using your graphing calculator is key. If your unit exam says justify your reasoning, make sure you actually give your reason. So which graph or which equation did you say is number 1? Q. Okay, so why did you say it was Q of x, Jesse? Why did you say this graph? Did you say it was Q as well? No? Okay, then listen up.
Yep, that's correct.
Okay, so why is it Q? Why not? So we're between Q and we're between H. What makes, they both have the same y-intercept. The only thing different is their slopes. So why is he Q and not H? Rise over run. So who has a steeper slope? Yeah, Q has a steeper slope. It's a larger number. Looking at the number, not the sign. 2 is bigger than a half. So this is a steeper line compared to this line. So because the slope here is negative 2 over 1, and the slope here, this would be H, is negative 1 over 2. It's not as steep. Okay, that takes care of those two. The next two here, 5 and 2. Andrew? Listen up, okay? It's between, it's a quadratic, right? They're quadratic. So it's between these two. Looking at the graph, what's the only thing that's different between these two equations? The y-intercept. So notice this y-intercept is at 1, and this y-intercept is at negative 2. And so what is our graph 5? K. Yep, K of x. So since the y-intercept is 1, and this guy would be your J, since the y-intercept is negative 2. Okay, our cubics. We have two cubics. Okay, how do we know which one is this graph for? It's which one? Who says P? Who says G? Okay, it's P. Why is it P? The leading coefficient is positive. If it rises to the right, it's a positive leading coefficient. Is positive, so that would be which guy? P. And last then, G, and why is that? Its leading coefficient is negative. Okay, it's negative because it's falling to the right. As we move to the right, it's falling. All right, Lucas, one more question. Lucas describes the characteristics of the following graph. Go away. Explain and correct Lucas' errors. Let's go through. This is a polynomial function of degree 3. Is that correct? Yeah, okay. So I know the graph will have 0 or 2 turning points. Is that correct? That is actually correct. So we know that the maximum number of turning points is 2, 1 less than degree. And with a cubic, it either has 0 would look like this, or 2 would look like this. Okay, so that's correct. The leading coefficient of this cubic is negative. Is that true? Yeah. Leading coefficient is in front of the x cubed. So I know the graph extends. So if it's negative, where does it start? 2, and then it goes to to what? 4. So is that correct? Quadratic 2 to 4? Yes. There is no constant term. Is that true? Yes, so there is no y-intercept. Is that true? No, that is false. There's still a y-intercept, but what is the y-intercept then? So that's his error. Error. That's his error. So what would be the y-intercept? If you have no constant term. It's there, but it's just plus what? No, 1 would change it. 0, which is 0. We don't write 0. So our y-intercept would be at the origin, is 0. That's his mistake. Because the function is cubic, I know that there can be 1, 2, or 3 x-intercepts. Is that true? Yes. So because the degree is 3, we have a maximum number of 3 x-intercepts. All right. So, quick review. What does a constant function look like? Linear, quadratic, and cubic. So if I had a constant, guys, just before you start, what type of line? Like y equals 3, what would that look like? What type of line? Straight. All lines are straight, so horizontal. That would be a constant. Oh, I know. There you go. Okay, linear, if I had y equals 3x plus 1, what would that look? Or minus 1? So the y-intercept would be -1 and a slope of 3. So it's also a line. It has degree of 1, but it actually has a slope. A quadratic, if you had y equals 3x squared, what would that look like? A U opening up. Okay, and a cubic, y equals 3x cubed plus 3x squared minus x plus 1. What would that look like? Couple humps. My lovely lady lump. Okay. That's what they are. They are kind of like humps, right? Humps. Okay. Now I'm embarrassed. Okay, so your homework is all of 5.2. So it's, yes, page 120 to 121. Yes, it is. So your homework is all of 5.2. No, don't remix that, please. 120 and 121. Wait, this is not page 120 and not 121. Okay.